Good morning, everyone. It's a real pleasure to introduce you to the BoilerWatch MMP2 system today. This technology, also known as an acoustic pyrometer, is an advanced solution specifically designed for viewing combustion heat maps. It's used to optimize operations in CT Trinitaria's fossil fuel boilers. We've been with CLEC since 2012, and we have 4 systems installed here in Ecuador. As the manufacturers of this innovative technology, we offer you our full support. With this tech, you'll be able to adjust burners, preventing damage to the tube walls. Our goal is to provide high-precision tools for unprecedented thermal monitoring. In this session, we'll explore how this technology transforms data collection into critical information for operational efficiency and the safety of your most valuable assets in national power generation. Our agenda for today is broken down into 4 key points for a complete understanding of the system. We'll start with the fundamentals of acoustic technology, followed by a detailed analysis of the current installation in your plants. Then, we'll dive into the capabilities of the TMS 2000 software, which is at the heart of our data processing. We'll also discuss its direct impact on combustion control. Let's dive into the tech itself. Here, we can see the 3 main components of the acoustic pyrometer. First, we have the sensors, which are installed on the external wall. Second, there's the processor, installed within 160 meters of the sensors. And third, the computer in the control room. Acoustic pyrometry is built on a fundamental and elegant physical principle. The speed of sound is directly proportional to the temperature of the gas it travels through. By precisely measuring the time it takes for a sound signal to travel from a transmitter to a receiver, the BoilerWatch system can calculate the average gas temperature along that specific path. This method gives us instant measurements in environments where traditional contact sensors would quickly fail due to extreme heat. Here, we can see a simulation of how the sound waves are sent. The system can manage up to 24 measurement paths, either vertical or horizontal, covering a wide area of the boiler. One of its biggest advantages is that it's non-intrusive, meaning no sensors inside the boiler. It operates with compressed air at 60 to 100 pounds of pressure to generate the acoustic pulses. Each measurement cycle finishes every 4 seconds, giving you near real-time data updates for operational control. You can place sensors on 2, 3, or even 4 walls. Data visualization is key. The system generates detailed horizontal maps and enables early leak detection. On screen, you'll see the trajectory map, the isothermal map showing heat distribution, and the area map. On the area map, red indicates higher than expected temperatures, blue is colder, and green is perfect. This information helps identify high temperature zones or imbalances. You'll notice the design accounts for both existing inspection doors and the new waveguides needed to fully cover the burner row. Now let's review the current installation section. It's crucial to understand how these components physically integrate into your plant to ensure optimal data collection. The correct placement and mounting of sensors determine the accuracy of the final thermal maps. In the next slides, we'll see real images of the installed equipment, which will help us audit the system's current state and plan any necessary improvements to the support infrastructure, cabling, and instrument air supply to the boiler. Here, we see the PCU. This cabinet is the electronic brain of the system. It houses the processing cards, communication modules, and power interfaces. As you can see in the photo, the internal layout is modular, which makes diagnosis and component replacement easy, should it ever be needed. The PCU receives electrical signals from the remote microphones, digitizes them, and performs time-of-flight calculations to determine the temperature of each path before sending them to the central software. In this technical diagram, we see the complete sensor assembly. The design includes the 3020TR preamplifier cabinet connected to the amplifier box. It details the plant air inlet, which is essential for the acoustic signal, and the waveguide connection via a standard 5-inch flange. The engineering behind this mounting ensures the microphone is thermally protected while maintaining a clear acoustic path into the boiler. It's a proven setup that minimizes background noise and maximizes the system's signal-to-noise ratio. In practice, this is how the sensors look installed on the boiler wall. On this unit, we have 8 strategically distributed sensors. The image shows the robustness of the mounting, with air and signal connections protected by flexible stainless steel hoses. Despite the dirt and radiant heat conditions outside, the sensor's design allows for continuous operation. It's vital to keep these areas clear of obstructions and periodically check for any air leaks in the connections to maintain measurement fidelity. A major innovation is our new waveguide, designed to offer greater temperature protection to the piezoelectric element. As the thermal measurements on screen show, while the external surface can be over 155 degrees Celsius, the new waveguide's design dissipates heat, keeping critical components at a much safer temperature of approximately 49.7 degrees. This difference of over 100 degrees is vital to prevent sensor degradation and extend preventive maintenance intervals in high thermal load areas. Here we see the amplifier boxes. They complement the sensors, and typically 8 amplifier boxes are installed, like the ones shown in this photograph. These boxes are mounted on the boiler's exterior walkways. Their main function is to receive the weak analog signal from the microphone and boost its power before sending it over long distances to the PCU. This step is crucial to prevent data loss or electromagnetic interference, which is common in industrial plants with large motors and high-voltage generators. Here we see the steps for a typical installation preparation. The process involves modifying the boiler wall to insert the waveguides, ensuring they align with the tubes. Adapter flanges and special seals are used to prevent combustion gases from escaping. In the small photos, you can see the final finish and how the sensor securely attaches to the structure. This precision work ensures the sound wave travels straight through the boiler section, avoiding false reflections from the internal walls. Moving into the mapping software, the TMS 2000 offers a variety of screens for the operator. These include the real-time thermal map, individual trajectory visualization, area maps divided by burner zones, historical trends, detailed statistics, internal noise monitoring, and, very importantly, wall temperatures. This intuitive graphical interface allows operating personnel to identify thermal anomalies in seconds, facilitating a rapid response to any deviation from the standard combustion process that could affect efficiency. This is the main view of the TMS 2000 software. Notice the information presented simultaneously. On a single screen, we have noise monitoring in the upper left corner, the isotherm map below, and the area map on the right, along with temperature trend graphs. The software processes thousands of data points per minute to generate these visualizations. The ability to see how these different variables interact allows plant engineers to understand the heat dynamics inside the boiler furnace in a way that was previously impossible. The isotherm screen is one of the most powerful tools. It displays lines of equal temperature, letting you visualize the shape and position of the flame's heat core. In this example, the map shows an average temperature of 950 degrees Celsius, with peak points near 1,300 degrees. You can also see the wall temperatures. By observing the symmetry on the map, these curves represent the same temperature. Operators can determine if combustion is centered or imbalanced, which could cause localized overheating in the wall tubes or upper superheaters. The software also lets you divide the boiler into up to 24 specific areas. Each cell on the map shows the average temperature for that particular zone. In this view, we can quickly spot if any burner is operating outside its normal parameters. For example, if we see a cell significantly colder or hotter than its neighbors, we can investigate issues with that specific burner's fuel or air supply. This is essential for fine-tuning combustion and maximizing the boiler's thermal efficiency. Here we can see good temperatures and area trends, which allows us to analyze the system's behavior over time. The 24 trajectories tell us the equipment is working at 100%. The graph of area trends shows how they've evolved over the last few hours. Trends are vital for identifying gradual changes that could indicate soot accumulation on tubes or changes in fuel quality. The stability of these lines directly indicates combustion stability inside the boiler, helping predict when soot blowing or air adjustments will be necessary. Leak detection is another critical capability of the TMS 2000. By constantly monitoring background noise at specific frequencies, the system can identify the characteristic sound of a steam leak in the tubes long before it's visible to operators or causes a significant pressure drop. The graph shows how a sudden increase in noise levels triggers an alert. Detecting a leak in its early stages allows for a scheduled, controlled shutdown, preventing catastrophic erosion damage to adjacent tubes and drastically reducing repair costs. The alarm system is highly configurable. In this case, we see an alarm notification for all 4 walls. When the system detects that temperatures in the 4 corners exceed safety limits or show excessive divergence, a visual and audible alert is triggered. This is fundamental for protecting the boiler's structural integrity. The graph on the right shows how the temperature steadily rose until it reached the alarm threshold, providing the operator with a clear early warning to take immediate corrective actions. Here we can see a high-temperature alarm on the wall. This is especially useful if a boiler zone is known to be prone to hotspots or has had previous repairs. In the image, we see how the system highlights the affected wall, allowing for localized intervention. By keeping wall temperatures within safe ranges, we reduce thermal stress on the metal and extend the lifespan of refractory materials and tubes, which means greater plant availability in the long term. During boiler startup, the TMS 2000 offers a suggested screen for monitoring heating progress. This view combines hourly statistics with wall temperature graphs and area maps. It's a critical period where thermal uniformity is vital to prevent mechanical deformation. Having precise data during startup allows for safer and more efficient full-load operation, ensuring all combustion systems come online in a balanced way, without dangerous thermal spikes in the initial stages. A key aspect we address is combustion balancing through managing soot blowing and leak detection. Acoustic pyrometry lets us see the immediate effect of soot blowers on gas temperature. If a soot blower isn't working correctly, the system will show that there's no expected temperature drop due to tube cleaning. This direct feedback allows for optimizing soot blowing cycles, saving steam and reducing tube wear from excessive blowing, all while maintaining maximum heat transfer efficiency. This graph shows the noise from soot blowers and steam leak feed. Here, in a refinery simulation, we can see a faulty burner and how the flame hits the wall. Burners, with their air registers and flow control, can be used to manage each burner's flame. This is visible in our TMS 2000 software. The ultimate goal is to move from an imbalanced state to a balanced one. The comparative images on screen clearly show the difference. On the left, we see an off-center heat core and uneven temperatures between areas. On the right, after adjustments made with the system's help, we observe a much more uniform and centered thermal distribution. Balanced combustion not only improves thermal efficiency but also reduces pollutant emissions like nitrogen oxides and minimizes slag formation in critical boiler zones. In conclusion, the BoilerWatch MMP2 system, in steam thermal and combined cycle power plants, provides the CT Trinitaria with a significant technological advantage for managing their boiler's thermal performance. Through acoustic pyrometry, we transform a hostile and obscure environment into a map of clear, actionable data. Thank you very much for your attention and for your commitment to the continuous improvement of power generation. We are at your entire disposal to delve into any technical detail or to discuss implementation in your units. Together, we will elevate the efficiency and safety of your operations. Thank you.